Let yourself settle in for a moment. Find that comfortable position where your body can truly relax, where the weight of the day begins to lift from your shoulders. Take a slow breath, feeling the air move through you, and as you exhale, let any tension drift away like smoke dispersing in the evening air. Tonight, we're going on a journey to the smallest planet in our solar system, a world of paradoxes and mysteries that scientists are only beginning to understand. Just close your eyes if you'd like, or let them rest gently on a distant point, and allow the story to unfold around you like a gentle tide. We're heading to Mercury, a planet so close to the Sun that you might expect it to be simple, well understood, a scorched rock with nothing left to discover. But you'd be wrong. Mercury is turning out to be one of the strangest worlds we've ever studied, a place where ice exists on the hottest planet in the solar system, where diamonds may hide deep beneath the surface, where the ground itself is wrinkling and cracking as the planet continues to shrink before our eyes, and where mysteries pile upon mysteries in ways that challenge everything we thought we knew about how planets work. Before we dive into these cosmic wonders, if you're enjoying this journey through the mysteries of our solar system, please consider subscribing to The Science Pillow and hitting that like button. Your support helps us continue creating these relaxing explorations of the universe's greatest mysteries. Now, breathe deeply. Let your mind wander among the stars, and let's discover what's really happening on Mercury, the closest mystery. Mercury orbits the Sun at an average distance of about 36 million miles. To put that in perspective, if the Sun were the size of a basketball sitting at center court, Mercury would be a BB pellet orbiting about 15 feet away. It's the closest planet to our star, completing one orbit every 88 Earth days, blazing through space at nearly 30 miles per second. You might think that being so close to home, being right there in our cosmic neighborhood, we'd know Mercury inside and out by now. After all, ancient astronomers could see it with their naked eyes, watching it dart back and forth across the twilight sky, appearing sometimes as a morning star, sometimes as an evening star. But proximity doesn't always mean accessibility. Mercury is, in many ways, the most difficult planet in the inner solar system to visit. The problem isn't distance. The problem is speed and the Sun's immense gravitational pull. Any spacecraft heading to Mercury must not only travel those 36 million miles, but it must also shed enormous amounts of orbital velocity to avoid simply whizzing past the planet or, worse, falling into the Sun. It's like trying to land a plane on a runway that's moving at highway speeds while you're traveling even faster. The energy required to slow down enough to enter Mercury's orbit exceeds the energy needed to reach the outer planets. This is why, despite more than 6 decades of space exploration, only 3 missions have ever visited Mercury. The first was Mariner 10, which conducted 3 flybys in 1974 and 1975, giving us our first close-up glimpses of this mysterious world. But Mariner only photographed about 45% of Mercury's surface, leaving more than half the planet shrouded in mystery for 3 more decades. The spacecraft discovered something completely unexpected. Mercury had a magnetic field, weak but definitely there, suggesting that this tiny world had a partially molten core, something scientists hadn't anticipated for such a small planet. The second visitor was MESSENGER, which stands for Mercury Surface, Space Environment, Geochemistry, and Ranging. Launched in 2004, MESSENGER didn't reach Mercury's orbit until 2011, after a 7-year journey involving multiple planetary flybys to shed enough speed. For 4 years, from 2011 to 2015, Messenger orbited Mercury, mapping its entire surface, studying its composition, measuring its magnetic field, and making discoveries that rewrote our understanding of this tiny world. When the spacecraft finally ran out of fuel in April 2015, mission controllers deliberately crashed it into Mercury's surface, where it created a new crater about 16 meters wide, leaving a permanent mark on the planet it had studied so thoroughly. Now, the third mission is on its way. BepiColombo, a joint European-Japanese endeavor, launched in October 2018, and has been conducting a series of planetary flybys to gradually work its way into Mercury's orbit. The spacecraft has already completed 6 close passes of Mercury, each one bringing back stunning images and valuable data. After a propulsion issue delayed the timeline, BepiColombo is now scheduled to enter Mercury's orbit in November 2026, where it will deploy 2 separate orbiters to study the planet from complementary perspectives. But why is it so hard to reach Mercury? The answer lies in orbital mechanics. Earth orbits the Sun at about 67,000 miles per hour. Mercury orbits at nearly 106,000 miles per hour. To reach Mercury from Earth, a spacecraft must somehow shed almost 40,000 miles per hour of velocity. Doing this with rocket fuel alone would require carrying so much propellant that the spacecraft would be impossibly heavy to launch. Instead, missions to Mercury use a technique called gravity assist, flying past other planets and using their gravitational fields like cosmic slingshots to gradually adjust speed and trajectory. BepiColombo, for example, flew past Earth once, Venus twice, and Mercury 6 times before finally having the right speed and trajectory to enter orbit. And then there's the heat. Mercury's surface temperature can reach 800 degrees Fahrenheit on the sunny side, hot enough to melt lead and zinc. Any spacecraft orbiting Mercury must endure not only this intense heat, but also the fierce solar radiation that bombards everything in Mercury's neighborhood. BepiColombo carries special heat shields and thermal radiators to dissipate this heat, and its solar panels must be angled carefully to avoid overheating while still collecting enough sunlight to power the spacecraft. So Mercury remains enigmatic, not because we haven't tried to explore it, but because getting there and surviving there pushes our technology to its limits. Every piece of data we've gathered from this world has been hard-won, which makes the discoveries all the more remarkable. And what we've discovered is that Mercury is nothing like what we expected. It's a world where extremes collide, where contradictions abound, and where every answer seems to raise 3 new questions. A planet of contradictions. If you were standing on Mercury's equator at local noon, when the sun reaches its highest point in the sky, the temperature around you would be scorching 800 degrees Fahrenheit. The sun would appear about 3 times larger in Mercury's sky than it does from Earth, a blazing furnace dominating your view. The ground beneath your feet would radiate heat upward, and you'd need protection not just from the temperature but from the intense ultraviolet and X-ray radiation pouring down from above. This is one of the hottest environments in the solar system, a place where most materials would melt, vaporize, or decompose. Now, let's walk just a few hundred miles toward Mercury's North Pole. As we approach the polar regions, the landscape changes. We start seeing craters, as we do everywhere on Mercury's heavily bombarded surface. But some of these craters are different. Their floors lie in permanent shadow, never touched by sunlight. Mercury's axis has almost no, tilt, less than 1 degree, which means that near the poles, the sun never rises more than 1 degree above the horizon. Deep crater floors at high latitudes never see direct sunlight. Ever. In these permanently shadowed regions, the temperature plummets. Without sunlight and without an atmosphere to distribute heat, these crater floors reach temperatures around minus 280 degrees Fahrenheit. And there, in these frozen pockets on the hottest planet in the solar system, scientists have discovered water ice. Lots of it. Billions of tons of frozen water, hiding in the shadows of a world that you'd expect to be completely parched. The first hints came in the early 1990s when radio telescopes on Earth detected highly reflective patches near Mercury's poles. Radar waves bounced off something bright in those shadowed craters, and ice was a prime suspect. But it seemed almost too bizarre to believe. How could ice survive on Mercury? Where did it come from? When Messenger entered orbit in 2011, it carried instruments that could test this hypothesis. Its neutron spectrometer detected signals consistent with hydrogen-rich materials in the polar regions. Its laser altimeter, designed primarily to map elevation, could also measure surface reflectance. Scientists found that the radar-bright regions lined up perfectly with permanently shadowed crater floors, and these regions reflected light in exactly the way you'd expect from water ice. Messenger's cameras, carefully aimed to catch sunlight reflecting into the shadowed regions during favorable orbital positions, revealed additional details about these icy deposits. The ice isn't pure. In some of the coldest craters, it appears to be exposed at the surface, pure water ice that would gleam white if we could somehow illuminate it. But in other craters, where temperatures are slightly higher though still well below freezing, the ice is covered by a dark layer of something else, something that absorbs nearly all the light that hits it. This dark material is thought to be a complex mixture of organic compounds, carbon-based molecules delivered to Mercury by comets and asteroids over billions of years. Think about that for a moment. The same impacts that delivered water to Mercury also delivered organic material, the building blocks of life as we know it. Trapped in these permanently frozen craters are not just ice, but also carbon compounds, all preserved in a deep freeze that has lasted for potentially billions of years. Some of these deposits may be ancient beyond imagination, accumulating slowly over the eons as micrometeorites carrying tiny amounts of water and carbon rained down on Mercury's poles. Recent studies have found that the ice deposits are more extensive than originally thought. Beyond the large craters, scientists have identified what they call micro-cold traps, small shadowed regions scattered across Mercury's polar areas. These might be small craters, or simply irregular terrain where shadows persist. Thermal modeling suggests that thousands of these micro-cold traps could exist, each one potentially harboring its own deposits of ice. If spread out and measured, Mercury's polar ice deposits might cover an area the size of Washington, D.C., with a thickness of more than 2 miles. That's a staggering amount of frozen water on a planet where you'd expect every last molecule to have boiled away billions of years ago. But the ice is just one contradiction. Mercury's magnetic field is another. Earth has a strong magnetic field generated by the motion of molten iron in its outer core, a dynamo process that creates a protective bubble around our planet, shielding us from the worst of the solar wind. Mars, similar in composition to Earth but smaller and cooler, has no global magnetic field today, though it did in the ancient past before its core cooled and solidified. Venus, nearly identical to Earth in size and composition, also has no magnetic field. Mercury is tiny, smaller even, than some of the solar system's moons. It has a diameter of just 3,030 miles, barely larger than our moon. With such a small size, Mercury should have cooled off long ago, its core solidifying, its internal dynamo shutting down. Yet it has a magnetic field, weak but measurable, about 1% of the strength of Earth's field. That's strong enough to deflect the solar wind and create a miniature magnetosphere around the planet. A small bubble of protection in the intense radiation environment so close to the sun. The existence of this magnetic field puzzled scientists for decades. In 2007, researchers used radar measurements to study how Mercury wobbles as it rotates, and they confirmed that the planet's core is at least partially molten. Something in that core, probably sulfur or some other light element mixed with the iron, has lowered the freezing point enough to keep the part of the core liquid even after 4.5 billion years. This liquid metal, moving and convecting in the planet's interior, generates the magnetic field through dynamo action, just as Earth's core does. But Mercury's magnetic field isn't like Earth's. For one thing, it's remarkably symmetric, aligned almost perfectly with the planet's rotational axis. Earth's field wobbles and wanders, its magnetic poles drifting over time, but Mercury's field is eerily stable and axisymmetric. Even stranger, the magnetic field appears to be offset from the planet's center, shifted northward by about 300 miles. It's as if the dynamo generating the field isn't centered in Mercury's core, but is displaced toward the northern hemisphere. Scientists have proposed various models to explain this offset. Maybe there's a stable, non-convecting layer at the top of Mercury's core, forcing the active dynamo region to be smaller and offset. Maybe the magnetic field is being influenced by the solar wind, which constantly buffets Mercury's magnetosphere with charged particles traveling at millions of miles per hour. Maybe Mercury's core has a complex, layered structure that we don't fully understand yet. Recent numerical simulations have shown that a self-regulating dynamo, where the magnetic field itself influences the convection that generates it, could produce the kind of offset field we observe. But these are models, mathematical approximations, and the truth probably involves processes we haven't yet imagined. In 2021, scientists analyzing messenger data made another intriguing discovery. They found a magnetic anomaly that coincides with a large topographic feature called the Northern Rise, a bulge on Mercury's surface about 600 miles wide. The magnetic signature appears to originate not from the crust but from deep within the planet, at or below the boundary between the core and the mantle. This suggests connections between Mercury's interior dynamics and its surface features, a coupling between the deep core and the thin mantle that we don't see on other planets. Mercury's mantle is only about 250 miles thick, compared to Earth's mantle of about 1,800 miles. This thin mantle might allow processes in the core to directly influence what happens at the surface in ways that would be impossible on larger worlds. And there's yet another magnetic mystery. Some young impact craters on Mercury show crustal magnetic anomalies, localized regions where rocks in Mercury's crust are magnetized. How did this happen? Mercury's surface is very low in iron, which is typically the best magnetic carrier material. Scientists think that iron-rich meteorites slammed into Mercury, delivering magnetic minerals that recorded the planet's magnetic field when the impact melt, cooled, and solidified. The asymmetric distribution of these anomalies around certain craters can even tell us the direction the impactor came from and the angle of impact. These frozen magnetic signatures, preserved in rock for hundreds of millions or billions of years, are time capsules containing information about Mercury's ancient magnetic field and its impact history. So, Mercury is a planet of extremes and contradictions. Ice on the hottest world, an active magnetic field in a body that should have frozen solid, temperature swings of over 1,000 degrees between day and night, ancient water and organic compounds preserved in eternal darkness, while the nearby surface bakes under the relentless sun. Every characteristic seems to defy expectations, and every answer we find leads to deeper questions about how this strange little world came to be, the shrinking world. Mercury is getting smaller. Not might be getting smaller. Not probably getting smaller. Is getting smaller right now as the planet continues to cool and contract, wrinkling its surface like an apple left too long in the fruit bowl. This ongoing shrinkage is one of the most remarkable recent discoveries about Mercury, evidence that even 4.5 billion years after its formation, this tiny planet is still geologically active. The first clues came from Mariner 10's photographs in the mid-1970s. Scientists noticed long, curved cliffs snaking across Mercury's surface, features they called lobate scarps. These scarps are exactly what you'd expect to see if a planet's interior was shrinking, forcing the surface crust to buckle and thrust upward. Imagine taking a ball of clay and somehow making the inside smaller while keeping the outside clay layer intact. The clay would have to wrinkle and fold to accommodate the reduced interior volume. That's what's happening to Mercury. When Messenger arrived and mapped the entire planet, it found lobate scarps everywhere, at all latitudes and longitudes, cutting across all types of terrain. Some of these scarps are enormous. Discovery Rupees, one of the most prominent, is a cliff face that rises more than half a mile high and stretches for over 600 miles across Mercury's surface. Victoria Rupees is similarly impressive. These scarps often cut through impact craters, showing that the shrinkage happened after the craters formed. But many craters are also superimposed on top of the scarps, suggesting that the scarps are ancient features. Most of them formed around 3 billion years ago, when Mercury's interior was cooling most rapidly. By measuring the heights and lengths of thousands of these scarps and using models of how planetary crusts respond to stress, scientists calculated that Mercury's diameter has shrunk by at least 7 miles over its history. More recent estimates, incorporating different types of surface features, suggest the total contraction could be anywhere from 9 to 14 miles. To put that in perspective, if Earth shrank by an equivalent proportion, its diameter would decrease by about 60 to 90 miles. That's a significant amount of contraction. But here's where it gets really interesting. For a long time, scientists assumed that this shrinkage was ancient history, that Mercury had done most of its contracting billions of years ago when it was young and hot, and that the process had essentially stopped. The scarps were fossil features, frozen evidence of ancient cooling, but not signs of ongoing activity. Then, in 2016, researchers examining the highest resolution messenger images noticed something new. Some of the scarps had small, fresh-looking fractures running across their crests. These fractures, called grabens, are narrow troughs that form when the ground is stretched and pulled apart. They might seem contradictory, stretching on a shrinking planet, but they make perfect sense. As thrust faults push one section of crust up and over another, the top of the thrust sheet bends, and this bending creates tension that can crack the rock, forming grabens. The crucial point is that these grabens are young. They're small, sharp, well-defined. On Mercury's surface, which is constantly being pelted by meteoroids, small surface features get blurred and erased over time through a process called impact gardening. Incoming debris kicks up dust that settles back down, gradually burying and softening features. The sharper and clearer a small feature is, the younger it must be. Based on the rate of impact gardening, scientists calculated that these grabens must be less than 300 million years old. Some might be much younger. That means the scarps have moved recently, in geological terms. The thrust faults beneath them are still active. Mercury is still contracting, still wrinkling, still adjusting to its cooling interior. This was a revelation. Scientists had thought Earth was the only tectonically active, rocky planet in the solar system, but now Mercury joins that exclusive club. In 2023, a comprehensive study mapped 48 large lobate scarps with definite grabens and 244 more with probable grabens, features that weren't quite clear enough in Messenger's images to confirm but looked very likely. These grabens are distributed globally, suggesting that Mercury's contraction isn't happening in just one region, but across the entire planet. The planet is shrinking more or less uniformly, though some regions do show more tectonic structures than others, possibly because of variations in crustal strength or thickness. This ongoing contraction has another implication: Mercury quakes. Just as the Moon experiences moonquakes from tidal stresses and thermal cycling, Mercury should experience quakes from the movement of these thrust faults. We haven't measured these quakes directly because we've never placed a seismometer on Mercury's surface, but the evidence is compelling. On the Moon, where we have seismic data from the Apollo missions, scientists have found that lobate scarps similar to Mercury's are associated with moonquakes. Fresh boulder tracks on the lunar surface, rocks that have rolled downhill recently, are often found near scarps, presumably dislodged by quakes. Could the same thing be happening on Mercury? BepiColombo's high-resolution cameras might reveal similar boulder tracks when the spacecraft enters orbit in 2026, providing indirect evidence of Mercury quakes. The fact that the planet is actively shrinking, that its faults are moving, strongly suggests that quakes are occurring. These wouldn't be the plate tectonic earthquakes we experience on Earth, driven by the collisions and subductions of massive crustal plates. Instead, they'd be contraction quakes, the groaning and cracking of a planet adjusting to its changing size. The mechanism driving Mercury's contraction is straightforward: thermal physics. As the planet's interior cools, the material inside becomes more dense and takes up less volume. The metal core, in particular, shrinks as it cools. Some scientists have also proposed that as Mercury's core cools, solid iron might be crystallizing and forming an inner core, releasing latent heat in the process but also causing the core to contract even more. This combination of thermal contraction and possible inner core growth could sustain Mercury's shrinkage for billions of years. But Mercury's shrinkage isn't uniform across the surface. Some regions show denser concentrations of tectonic features than others. The northern volcanic plains, vast expanses of ancient lava flows, show particularly abundant evidence of contraction. This might be because the volcanic rocks in these regions have different strengths and failure properties compared to heavily cratered terrain. Or it might reflect variations in crustal thickness or the presence of pre-existing weaknesses that made it easier for faults to form. The discovery that Mercury is still tectonically active changes how we think about small planets. For decades, the conventional wisdom was that small worlds cool quickly and die geologically, becoming inert balls of rock within their first billion years. Mercury, by all rights, should have frozen solid long ago. Yet here it is, still moving, still changing, still very much alive in a geological sense. This has implications for how we think about other small bodies in the solar system and beyond. If Mercury can remain active for 4.5 billion years, maybe other small worlds can too, under the right conditions. As BepiColombo prepares to enter orbit, one of its key objectives will be to study Mercury's tectonic features in unprecedented detail. The spacecraft carries cameras capable of resolving features just a few meters across, which should reveal small grabens and other young tectonic structures that Messenger couldn't see. By mapping these features and studying their distribution, scientists hope to understand exactly how fast Mercury is contracting today and whether the rate is changing over time. They'll also be able to look for evidence of very recent fault movements, perhaps even features that formed within the last few million years. The story of Mercury's shrinkage is a reminder that planets are not static objects. They're dynamic, evolving systems, shaped by processes that can span billions of years. Even now, as you listen to these words, Mercury is cooling, contracting, its surface creasing and folding in slow motion. In another billion years, when the sun has grown slightly brighter and Earth's oceans have begun to evaporate, Mercury will be smaller still, its surface crossed by new scarps, its interior a bit cooler, a bit denser, continuing its long, slow march toward becoming a cold, dead world. But that day is still unimaginably far in the future. For now, Mercury lives, the diamond discovery. Deep beneath Mercury's surface, hidden below hundreds of miles of rock and metal, there may exist a layer of diamonds up to 15 miles thick. Not diamond dust, not scattered crystals, but a continuous shell of solid diamond wrapped around the boundary between Mercury's rocky mantle and its enormous metallic core. This isn't science fiction. It's a serious scientific proposal based on cutting-edge experiments and our growing understanding of how Mercury formed. And, if it's true, it could help explain some of the planet's most puzzling characteristics. The story begins with carbon. Messenger discovered extensive deposits of graphite on Mercury's surface, particularly in certain dark regions that reflect very little sunlight. Graphite is pure carbon, the same material in your pencil lead, and its presence on Mercury was unexpected. The leading hypothesis is that early in Mercury's history, the entire planet was covered by an ocean of molten rock, a magma ocean, similar to what Earth and the Moon experienced after their formation. In this roiling sea of liquid rock, carbon would have been dissolved. As the magma ocean cooled and crystallized, forming Mercury's mantle and crust, carbon would have separated out. Being less dense than the silicate minerals forming the mantle, the carbon would have floated upward, eventually accumulating at the surface as a thin layer of graphite. This graphite flotation crust would have been pockmarked and disrupted by billions of years of impacts, but remnants survive today, visible in Messenger's spectroscopic measurements. The presence of all this carbon tells us something important. Mercury's magma ocean was saturated in carbon. There was so much carbon dissolved in the molten rock that it couldn't all stay in solution and had to precipitate out. This makes sense given Mercury's location. Forming so close to the Sun, Mercury would have been built from materials that condensed at high temperatures in the early solar nebula, and these materials tend to be rich in carbon relative to oxygen. Now, here's where diamonds enter the picture. In 2024, a team of researchers from Belgium and China published a study that used high-pressure experiments to simulate conditions inside Mercury. They created synthetic mixtures similar in composition to Mercury's mantle material, and subjected them to the kinds of pressures and temperatures that would exist at the boundary between Mercury's mantle and core, about 300 miles below the surface. The pressure at this depth is estimated at 7 gigapascals, more than 70,000 times Earth's surface atmospheric pressure. The temperature is around 2,200 degrees Fahrenheit. Under these conditions, something interesting happens. If the molten mantle was saturated with carbon and also rich in sulfur, as Mercury's interior appears to be, the carbon doesn't remain as graphite. Instead, it transforms into diamond. The sulfur lowers the crystallization temperature of the silicate minerals in the mantle, creating conditions where diamond is the stable form of carbon rather than graphite. As Mercury's core began to crystallize, forming a solid inner core deep within the liquid outer core, more diamonds would have formed from carbon dissolved in the metallic liquid. Because diamond is less dense than liquid iron, these diamonds would have floated upward through the core, accumulating at the core mantle boundary. The computer models suggest that this process would have created a diamond layer averaging about 9 to 15 miles thick, depending on exactly how much carbon was present and how efficiently it separated from the mantle and core. To put that in perspective, if we could somehow extract and cut these diamonds, we'd have quintillions of carats, enough to make everyone on Earth fabulously wealthy in diamond bling. Of course, we can't extract them. They're buried under 300 miles of solid rock, in a high-pressure, high-temperature environment that would destroy any drilling equipment we could conceivably build, on a planet where surface temperatures reach 800 degrees, and there's no air to breathe. But beyond the sheer coolness of Mercury having a diamond layer, this discovery has real scientific significance. For one thing, it could help explain Mercury's magnetic field anomalies. Diamond is an excellent conductor of heat, far better than the silicate rocks that make up most of the mantle. A diamond layer at the core mantle boundary would efficiently transport heat from the core into the mantle, creating strong temperature gradients that could drive more vigorous convection in the core. More vigorous convection means a more active dynamo, potentially explaining how such a small planet can maintain a magnetic field at all. The diamond layer might also influence Mercury's cooling history. By conducting heat away from the core efficiently, the diamond layer could have accelerated Mercury's cooling, causing the interior to solidify faster than it otherwise would. This rapid cooling might explain why Mercury's major phase of volcanism ended so abruptly around 3.5 billion years ago. Most rocky planets show volcanic activity lasting much longer, but Mercury's volcanoes seem to have shut down early. If the diamond layer helped cool the interior quickly, it would have reduced the amount of partial melting in the mantle, cutting off the supply of magma that feeds volcanoes. The researchers who made this discovery also noted that the same process could occur on carbon-rich exoplanets orbiting other stars. Mercury formed close to the Sun, where temperatures were high and carbon was abundant relative to oxygen in the solid materials condensing from the solar nebula. Exoplanets forming in similar conditions around other stars might also develop diamond layers. If we could somehow detect these diamond layers remotely, perhaps through their effects on a planet's cooling rate or magnetic field, it would give us a new window into the interior compositions and formation histories of worlds light years away, But we should be clear. The diamond layer on Mercury is still a hypothesis, not a confirmed fact. We haven't directly detected it. We can't drill down to check. What we have are experiments showing that diamonds would form under the right conditions, models suggesting Mercury had those conditions, and surface observations indicating that Mercury was rich in carbon. It all fits together logically, but science demands verification. BepiColombo may provide crucial evidence. One of the mission's key objectives is to measure Mercury's gravitational field with high precision. The way a planet's gravity varies across its surface reveals information about the distribution of mass in its interior. A thick diamond layer would have slightly different density than the surrounding mantle material, and this might create subtle gravitational anomalies that BepiColombo's instruments can detect. The mission will also study the planet's topography and how it relates to the underlying structure, potentially revealing whether the diamond layer affects the elevation of the surface above it. Another line of evidence might come from studying Mercury's thermal evolution. If the diamond layer exists and has been conducting heat efficiently, it would have influenced how fast different parts of the planet cooled, which in turn would affect the timing and distribution of volcanic activity, tectonic features, and other geological processes. By mapping these features in detail and comparing them with computer models of planetary cooling with and without a diamond layer, scientists can test whether the diamond hypothesis makes better predictions than alternative models. There's also a possibility, however remote, that some of Mercury's volcanic eruptions might have brought tiny diamonds to the surface. On Earth, certain rare volcanic rocks called kimberlites are famous for containing diamonds formed deep in the mantle. These eruptions are violent and fast, bringing mantle material to the surface so quickly that the diamonds don't have time to transform back into graphite. If similar explosive eruptions occurred on Mercury, they might have transported microscopic diamonds from the deep mantle to the surface. BepiColombo's spectrometers might be able to detect the spectroscopic signature of diamond in certain volcanic deposits, providing direct evidence that diamonds exist inside Mercury. The diamond layer idea is elegant because it ties together several of Mercury's mysteries. The unusual carbon-rich composition, the presence of a magnetic field in such a small planet, the early cessation of volcanic activity. All of these could be connected to the same underlying cause. A shell of crystallized carbon wrapped around Mercury's core, conducting heat, influencing convection, shaping the planet's evolution in ways we're only beginning to understand. Whether it's ultimately proven correct or not, the hypothesis illustrates how creative thinking and rigorous experimentation can shine light into the darkest, most inaccessible parts of distant worlds, the enormous iron heart. If you could somehow peel away Mercury's rocky exterior like removing the shell from a boiled egg, you'd reveal one of the strangest sights in the solar system. A ball of metal so large that it makes up about 85% of the planet's radius and roughly 60 to 70% of its total mass. Mercury's core is disproportionately enormous, far larger relative to the planet's size than the core of any other rocky world we know. This massive iron heart is one of Mercury's defining characteristics, and it's also one of its greatest mysteries. To understand just how unusual this is, let's compare Mercury to Earth. Earth's core makes up about 15% of our planet's volume and 32% of its mass. The core is substantial, providing the raw material for our protective magnetic field, but it's surrounded by a thick mantle of rock that extends 1/800 miles from the core mantle boundary to the surface. Mercury, in contrast, has a metal core about 2,200 miles in a diameter, wrapped in a rocky mantle and crust that together are only 250 to 300 miles thick. If Earth had Mercury's proportions, our core would extend to within 200 miles of the surface, and the continents and oceans would rest on just a thin veneer of rock above that enormous metallic sphere. This raises an obvious question. How did Mercury end up this way? Why is it so metal-rich compared to the other terrestrial planets? There are three main hypotheses, each with its supporters and each with implications for understanding not just Mercury, but the violent early history of the entire solar system. The first hypothesis is called the vaporization model. In this scenario, Mercury formed roughly the same way as the other terrestrial planets, accreting from the disk of dust and gas that orbited the young Sun. But Mercury's proximity to the Sun exposed it to intense heat and radiation. The intense solar energy could have preferentially vaporized the lighter silicate materials that form rocky mantles while leaving behind the heavier iron that forms cores. Over millions of years, this selective vaporization would strip away much of Mercury's rocky exterior, leaving the metal-rich core relatively intact. Picture standing on the beach watching waves erode the sand but leave larger rocks behind. The Sun's energy would have acted like cosmic waves, carrying away the lighter elements but leaving the heavy metals. This hypothesis has some appeal because it's straightforward and doesn't require any catastrophic events beyond the normal processes of planet formation. However, it faces challenges. Calculations suggest that even this close to the Sun, the temperature wouldn't have been quite high enough to vaporize rock efficiently over the timescales involved. Also, if this were the dominant process, we'd expect to see a gradient, with planets closer to the Sun being progressively more metal-rich. But Venus, the second planet from the Sun, has a metal fraction similar to Earth's, not intermediate between Earth and Mercury. The second hypothesis invokes a giant impact. In this scenario, Mercury initially formed with normal proportions, a metal core surrounded by a substantial rocky mantle like the other terrestrial planets. But early in its history, perhaps around 4 billion years ago during the chaotic period astronomers call the Late Heavy Bombardment, Mercury collided with another large object, perhaps a third or half Mercury's size. The impact would have been catastrophic, obliterating both bodies in a spray of vaporized rock and metal. But metal behaves differently than silicate rock in these collisions. The metal tends to reaccrete more efficiently, clumping together under its own gravity, while much of the silicate vapor escapes or is blown away by the solar wind. When Mercury reassembled from the debris, it would have retained most of its iron but lost a significant fraction of its rocky mantle. This idea has parallels with Earth's moon, which is thought to have formed from a giant impact between proto-Earth and a Mars-sized body called Theia. That collision vaporized both objects' mantles and ejected enormous amounts of material into orbit, which eventually coalesced into the Moon. If a similar, but even more energetic collision happened to Mercury, it could explain the planet's unusual composition. Evidence supporting this hypothesis includes Mercury's surface chemistry. Messenger found that Mercury's crust is rich in sulfur, potassium, and sodium, elements that are volatile and would normally evaporate at high temperatures. If Mercury had experienced extreme vaporization from solar heating, these volatiles should be depleted. But they're not. They're actually more abundant than on the Moon or even parts of Earth. This suggests that while Mercury may have lost its outer mantle, it didn't lose it through slow vaporization. A giant impact, which would have happened quickly and violently, could have stripped away the mantle while allowing the planet to retain some of its volatile elements in the remaining material. The third hypothesis suggests that Mercury's composition reflects the original building blocks from which it formed. In this model, the inner solar system near the Sun contained a higher proportion of metal-rich materials from the start. When planets assembled from these building blocks, Mercury naturally ended up more metal-rich than planets farther out. This could happen if the solar nebula, the disk of gas and dust from which the planets formed, was chemically stratified, with different regions having different compositions. Computer simulations of planet formation show that planets don't necessarily form exactly where they end up. Many simulations suggest that the terrestrial planets migrated significantly during their formation, moving inward or outward in response to gravitational interactions with each other and with the gas in the nebula. If Mercury formed from particularly metal-rich material, or if it migrated into the inner solar system from elsewhere, it could have acquired its unusual composition without requiring a catastrophic impact. Each of these hypotheses makes different predictions about Mercury's detailed properties, and each has strengths and weaknesses. The vaporization model struggles to explain the presence of volatile elements. The giant impact model requires a very specific type of collision to work, and the odds of such a collision happening at just the right time and with just the right energy seem fairly low, though not impossible. The selective accretion model needs special conditions in the early solar nebula that we can't verify directly. Most researchers currently favor some combination of the giant impact and selective accretion ideas. Mercury probably did form from somewhat metal-rich building blocks, and it may also have experienced a major impact that removed a significant portion of its mantle. Both processes could have contributed to creating the unusually metal-rich world we see today. What we know for certain is that Mercury's core is not just large but also unusual in other ways. Radar observations and analysis of Mercury's gravitational field have revealed that the core is partially molten. This was a surprise. For a small planet to retain a liquid core after 4.5 billion years, it needs some mechanism to slow down cooling, or to have a lower melting point for the core material. The current best explanation is that Mercury's core contains a significant amount of sulfur, perhaps 5 to 7% by weight, mixed in with the iron. Sulfur dramatically lowers the melting point of iron. Pure iron would be solid at the pressures and temperatures in Mercury's core, but iron sulfide remains liquid, allowing the dynamo process that generates Mercury's magnetic field to continue. Recent models suggest that Mercury's core has a layered structure. At the very center, there may be a solid, inner core of pure iron or iron-nickel alloy, where the pressure is high enough to force crystallization despite the presence of sulfur. Surrounding this solid inner core is a liquid outer core of iron sulfide, the active dynamo region where convection generates the magnetic field. Some models even propose a third layer, a solid or semi-solid layer at the top of the core where iron sulfide has partially crystallized, creating a snow of iron-sulfur crystals that sink slowly downward. This three-layer structure could help explain some of Mercury's magnetic peculiarities, including the offset of the magnetic dipole. The exact size and composition of each layer remain uncertain. BepiColombo will help constrain these parameters by measuring Mercury's gravitational field with unprecedented precision. Tiny variations in gravity as the spacecraft orbits reveal how mass is distributed inside the planet. By analyzing these variations, scientists can determine the size of the core, the warsta thickness of the mantle, and possibly even detect the boundary between the solid inner core and liquid outer core, if it exists. Another crucial measurement will be Mercury's libration, a slight wobbling in its rotation caused by the gravitational pull of the Sun. The amount of libration depends on the distribution of mass inside the planet. A planet with a fully solid interior would librate differently than one with a liquid core, and the exact pattern of libration can reveal the size and density of the liquid regions. Messenger made the first measurements of Mercury's libration, confirming that the core is at least partially molten, but BepiColombo's more sensitive instruments should refine these measurements significantly. Understanding Mercury's enormous iron core isn't just about solving a puzzle on one small planet. It has implications for understanding how all terrestrial planets form and evolve. If giant impacts can dramatically alter a planet's composition, then the planets we see today might be very different from the planets that initially formed. Earth itself experienced at least one major impact that formed the Moon, and would have significantly affected our planet's composition and evolution. Mars may have experienced impacts that stripped away part of its atmosphere and reshaped its surface. Venus, shrouded in thick clouds and with a surface we can barely see, might have its own impact history that shaped its evolution. Mercury represents an extreme case, a planet where the normal processes of formation and evolution were pushed to their limits. By studying this extreme, we learn about the range of possibilities, the different paths that planetary evolution can take, and we learn that planets are not fixed, predetermined objects. They're the products of chaos and violence, chance and necessity, shaped by processes both gradual and catastrophic over billions of years. Mercury's enormous iron heart is a testament to these processes, a reminder that even the smallest worlds can harbor the grandest mysteries. Water in hell. Let's return to Mercury's ice, because the story goes deeper than just frozen water hiding in shadowed craters. The full picture reveals a world where the most unlikely places have become preserves of ancient materials, cosmic time capsules that have captured and held on to volatile substances for potentially billions of years. When Messenger first confirmed the presence of water ice near Mercury's poles, the discovery raised an immediate question. Where did the water come from? Mercury has no atmosphere to speak of, just a thin exosphere of atoms blasted off the surface by solar radiation and meteoroid impacts. Without an atmosphere, water vapor can't exist for long on Mercury. Any water molecule freed from the surface would either be broken apart by ultraviolet light or would simply drift away into space. So, how did billions of tons of ice accumulate in Mercury's polar craters? The answer lies in impacts. Throughout the solar system's history, comets and asteroids have rained down on all the planets. Comets, in particular, are essentially dirty snowballs, mixtures of ice and rock that formed in the cold outer reaches of the solar system. When a comet impacts a planet, it delivers not just rock and metal but also water, along with various other volatile compounds. Most of this water would quickly be lost on a world like Mercury, evaporating and escaping to space within hours or days of the impact. But the permanently shadowed craters at Mercury's poles are different. Because Mercury's axis is tilted by less than 1 degree, the Sun never rises more than 1 degree above the horizon at the poles. Deep craters in these regions have floors that never see direct sunlight. Without sunlight and without an atmosphere to distribute heat, these crater floors become incredibly cold, reaching temperatures around minus 280 degrees Fahrenheit or lower. At these temperatures, water ice is stable. It doesn't sublimate, doesn't evaporate, it just sits there, frozen, solid, accumulating slowly over eons. Every time a comet impacts anywhere on Mercury, it delivers some water. Most of this water is lost, but a tiny fraction finds its way to the poles, either through the brief presence of a temporary impact-generated atmosphere that redistributes volatiles, or through a process called ballistic transport, where ice particles kicked up by impacts follow parabolic trajectories that can carry them thousands of miles before they land. If even a tiny percentage of the water molecules released by impacts over billions of years made their way to the permanently shadowed craters and became trapped there, the accumulated deposits would be substantial. Computer models of this process show that it works. Simulations that track water molecules hopping across Mercury's surface, released by impacts or by the slow breakdown of minerals under solar radiation, consistently show that a significant fraction ends up in the polar cold traps. The models match the observed distribution of ice remarkably well, with the thickest deposits in the coldest craters and thinner deposits in regions that are cold but not quite as frigidly frozen. But water isn't the only thing hiding in Mercury's polar shadows. Messenger's instruments also detected hydrogen-poor materials mixed with the ice, substances that don't reflect radar waves well but that absorb nearly all light, making them appear extremely dark. Spectroscopic analysis suggested these dark materials are complex organic compounds, carbon-based molecules similar to those found in the darkest asteroids and comets. The presence of organics on Mercury is fascinating because these are the building blocks of life as we know it. They're not alive, not even close, but they contain the kinds of molecules that, under the right conditions on other worlds, could have contributed to the chemistry that eventually led to life. On Mercury, these organics are frozen solid, preserved in a deep freeze that has lasted for, potentially, billions of years. In some ways, Mercury's polar deposits are among the most pristine samples of ancient comet material in the inner solar system, better preserved than anything we might find on Earth, where geological processes and the presence of liquid water would have long since altered or destroyed such materials. The distribution of ice and organics across Mercury's poles is complex. In the very coldest craters, where temperatures never exceed about minus 280 degrees Fahrenheit, pure water ice appears to be exposed directly at the surface. These deposits are bright in radar observations and would appear white if we could somehow see them in visible light. In slightly warmer areas, where temperatures might reach minus 250 degrees Fahrenheit, the ice is covered by a layer of darker material, the organic-rich compounds that insulate the ice below and prevent it from sublimating. This temperature-dependent distribution tells us something important. Mercury's polar deposits are stable under current conditions, but they're also sensitive to changes. If Mercury's axis tilt were to change even slightly, some of the currently shadowed regions would receive sunlight, and the ice there would sublimate and be lost. Conversely, if the tilt increased, new cold traps might appear, allowing ice to accumulate in currently unprotected regions. Over very long timescales, Mercury's axis tilt does change, oscillating by small amounts due to gravitational perturbations from the other planets. These changes happen slowly, over millions of years, but they could gradually shift the locations of the cold traps. Some of the ice we see today might be extremely ancient, deposited billions of years ago when the cold traps were in slightly different locations, while other deposits might be geologically young, accumulating within just the last few 100 million years. One of the most intriguing recent discoveries about Mercury's ice came from detailed mapping of the microcold traps, small shadowed regions scattered across the polar areas beyond the large craters. These microcold traps might be tiny craters only a few meters across, or they might be simple irregularities in the terrain where shadows persist. Thermal modeling suggests that thousands of these features could exist, each one potentially harboring small deposits of ice. The significance of the microcold traps is that they greatly expand the total area where ice can be preserved. The large, well-known, permanently shadowed craters were thought to contain most of Mercury's ice, but if thousands of smaller cold traps also have ice, the total amount could be substantially higher than originally estimated. Some calculations suggest that when microcold traps are included, the total volume of ice on Mercury could rival or even exceed the amount of ice at the Moon's poles, which has been a target for future human exploration, because ice could be processed into drinking water, breathable oxygen, and even rocket fuel. Could Mercury's ice ever be useful for human exploration? It's an interesting question. Mercury is about as hostile an environment as you can imagine for humans. The surface temperature swings, the intense radiation, the lack of atmosphere, and the sheer difficulty of getting there make Mercury one of the least likely destinations for human missions in the foreseeable future. But if we ever did establish a presence on Mercury, perhaps robotic research stations or automated mining facilities, the polar ice would be invaluable. It would provide the same resources that lunar ice might provide, but in a location where solar power is more abundant and where certain unique scientific opportunities exist. BepiColombo will study Mercury's ice deposits in more detail than ever before. The mission carries instruments that can map surface composition at high resolution, potentially identifying specific minerals and organic compounds. It will also measure temperatures across the polar regions with precision, helping to determine exactly which areas are cold enough to retain ice and which are just barely too warm. And it will search for new cold traps, both large craters that Messenger might have missed, and smaller features that couldn't be resolved in earlier data. There's also a possibility, though still speculative, that some of Mercury's craters might contain not just water ice but other frozen volatiles. Carbon dioxide, ammonia, methane, even more complex organic molecules could be preserved in the coldest regions. Comets contain all of these substances, and if they were delivered to Mercury and trapped in the polar cold traps, they would remain frozen indefinitely. Detecting these materials would require detailed spectroscopic observations that BepiColombo might be able to provide. The story of water ice on Mercury is a reminder that the universe is full of surprises, that nature doesn't always respect our intuitions about how things should be. The hottest planet harbors ice. The driest world preserves water. The most irradiated surface in the inner solar system safeguards organic molecules. These paradoxes aren't contradictions. They're lessons in the complexity and richness of planetary environments, demonstrations that even the most extreme worlds can have hidden depths, secret places where conditions are utterly unlike what we'd expect from the surroundings. Magnetic mysteries, deepening. We've touched on Mercury's magnetic field already, but as BepiColombo approaches and new analyses of messenger data continue, the magnetic mysteries are deepening rather than resolving. What scientists thought they understood about Mercury's magnetism is giving way to a more complex and, frankly, more puzzling picture. Let's start with what makes Mercury's magnetic field so strange. First, it's weak, about 1% the strength of Earth's field. Second, it's nearly perfectly aligned with Mercury's rotation axis, showing an axis symmetry that Earth's wandering magnetic field doesn't possess. Third, it's offset northward by about 300 miles from the planet's center, as if the dynamo generating it isn't centered in the core but is displaced toward one hemisphere. For years, scientists proposed various models to explain these features. One popular idea was that Mercury's dynamo operates in a thin shell at the top of the liquid core, with a stable, non-convecting layer above it, preventing convection closer to the core mantle boundary. This could produce a weak field, and might explain the northward offset if the convecting shell was thicker in one hemisphere than the other. But in 2019, researchers analyzing messenger data in detail discovered something that complicated this picture. They found localized magnetic anomalies in Mercury's crust, regions where rocks are magnetized far more strongly than the average crustal magnetization. The strongest of these anomalies is located in the northern hemisphere and appears to extend deep into the mantle, possibly all the way to the core mantle boundary. This feature, associated with a topographic rise on Mercury's surface called the northern rise, suggests that Mercury's interior is more heterogeneous than expected. The northern rise itself is puzzling. It's a region about 600 miles across where the surface elevation is significantly higher than the surroundings. Some researchers think it might be the scar of an ancient giant impact, a massive collision that created the Caloris Basin on the opposite side of the planet. When the impact occurred, shock waves would have traveled through Mercury's interior, converging on the antipodal point, the spot exactly opposite the impact site. The focused energy could have disrupted the crust and mantle, creating the rise and possibly affecting the magnetic properties of the deep interior. If this interpretation is correct, then Mercury's magnetic field is influenced not just by the dynamo in the core, but also by the geological scars of ancient impacts. The magnetization at the core mantle boundary beneath the northern rise might interact with the field generated by the dynamo, creating the offset we observe. This would mean that Mercury's surface history and its deep interior dynamics are coupled in ways we don't see on other planets, a consequence of Mercury's thin mantle allowing surface processes to directly influence the deep interior. Another magnetic mystery emerged from studies of how Mercury's magnetic field interacts with the solar wind. The solar wind is a stream of charged particles, mostly protons and electrons, flowing outward from the Sun at speeds of several hundred miles per second. When this wind encounters a planet with a magnetic field, it gets deflected, creating a bubble around the planet called a magnetosphere. Earth's magnetosphere is large and robust, extending tens of thousands of miles into space, providing significant protection from the solar wind. Mercury's magnetosphere is tiny by comparison, extending only about 1,000 miles above the surface on the day side and compressed to just a few hundred miles in some regions. The solar wind constantly buffets this small magnetosphere, sometimes compressing it so much that the planet's surface is directly exposed to the incoming particles. Messenger observed these compression events, called magnetospheric substorms, happening frequently. During substorms, charged particles from the solar wind can reach Mercury's surface, sputtering atoms off the ground and contributing to the planet's exosphere. These events also induce electric currents in Mercury's interior, which can be detected as magnetic fluctuations. By studying these induced currents, scientists can learn about the electrical conductivity of Mercury's mantle and crust, which in turn reveals information about composition and temperature. One surprising finding from these studies is that Mercury's mantle appears to be more electrically conductive than expected. This could mean the mantle contains more iron than scientists thought, or it could indicate the presence of other conductive materials like graphite, or, intriguingly, sulfides. The enhanced conductivity might also be related to the proposed diamond layer. While diamond itself is an electrical insulator in its pure form, diamond containing impurities or defects can be conductive. The magnetic field's interaction with the solar wind also creates phenomena visible in Mercury's exosphere. Messenger observed bright spots of sodium emission near the poles, correlated with regions where the magnetic field funnels solar wind particles down toward the surface. These particles impact the surface, sputtering sodium atoms into the exosphere where they glow brightly when excited by solar radiation. The pattern of these emissions changes with Mercury's position in its orbit and with variations in solar wind intensity, creating a dynamic, ever-shifting display visible to instruments that can detect sodium's characteristic yellow light. Recent theoretical work has proposed that Mercury's weak magnetic field might actually be self-regulating. In this model, the dynamo in Mercury's core generates a magnetic field, but this field then influences the convection patterns that generate it. If the field becomes too strong, it suppresses convection, weakening the dynamo. If it becomes too weak, convection increases, strengthening the dynamo. The system reaches a balance where the field is weak but stable, oscillating around an equilibrium state. This self-regulating dynamo could explain why Mercury's field is so much weaker than Earth's, despite both planets having active core dynamos. The model makes specific predictions about how Mercury's magnetic field should vary over time and how it should respond to changes in the solar wind. BepiColombo will test these predictions by monitoring the magnetic field continuously over the course of its mission. The spacecraft actually consists of two separate orbiters that will operate in complementary orbits, allowing simultaneous measurements from different locations. By comparing measurements from both orbiters, scientists can separate temporal variations in the field from spatial variations, something that wasn't possible with Messenger's single spacecraft. BepiColombo will also investigate whether Mercury's magnetic field shows any signs of polarity reversals, like the magnetic field reversals that Earth experiences every few 100,000 years. On Earth, these reversals are recorded in volcanic rocks that solidify while the field is in different orientations, creating a stratigraphic record of the field's history. Mercury's surface is ancient and heavily cratered, with volcanic rocks dating back billions of years. If Mercury's field has reversed in the past, some of these ancient volcanic flows might be magnetized in opposite directions compared to others. BepiColombo's magnetometer, which is more sensitive than Messenger's, might be able to detect these ancient remnant fields and determine whether Mercury's dynamo has flipped its polarity over geological time. There's also the question of how long Mercury's dynamo can keep running. The planet is small, cooling rapidly, and its liquid core is slowly solidifying. At some point, perhaps 1 billion years from now, perhaps sooner, the core will freeze completely and the dynamo will shut down. Mercury will lose its magnetic field, and the planet's surface will be fully exposed to the solar wind without any magnetic protection. The solar wind will erode the exosphere more efficiently, and the pattern of surface weathering will change, In this distant future, Mercury will become even more moon-like than it already is, a dead world with no internal activity and no magnetic shield. But that future hasn't arrived yet. For now, Mercury's dynamo continues to churn, generating its weak but persistent magnetic field, creating a miniature magnetosphere that struggles valiantly against the relentless onslaught of the solar wind. Every measurement we make of this field, every observation of how it fluctuates and responds to changing conditions, brings us closer to understanding the deep interior processes of this enigmatic world. BepiColombo's Journey. On October 20th, 2018, a rocket lifted off from Europe's spaceport in French Guiana, carrying one of the most ambitious planetary missions ever attempted. BepiColombo, named after Italian mathematician and engineer Giuseppe BepiColombo, who helped plan the trajectory for the Mariner 10 mission, began its 7-year journey to Mercury. The mission is a collaboration between the European Space Agency and the Japan Aerospace Exploration Agency, bringing together expertise from across the globe to study the solar system's innermost planet. BepiColombo isn't a single spacecraft. It's actually a complex stack of 3 separate modules that traveled together through space before separating at Mercury. The European Mercury Transfer Module provided the propulsion for the journey, using a combination of solar electric ion drives and gravity assists to gradually work its way into Mercury's orbit. The European Mercury Planetary Orbiter, or MPO, will study Mercury's surface and interior with cameras, spectrometers, radar, and other instruments. The Japanese Mercury Magnetospheric Orbiter, or MAIO, will study Mercury's magnetic field and its interactions with the solar wind using magnetometers, particle detectors, and plasma wave instruments. The journey to Mercury is not a straight shot. Remember, getting to Mercury requires shedding enormous amounts of orbital velocity, and doing this efficiently requires a carefully choreographed dance with the planets. BepiColombo's trajectory included 1 flyby of Earth in April 2020, 2 flybys of Venus in October 2020 and August 2021, and 6 flybys of Mercury itself before finally entering orbit. These Mercury flybys weren't just navigation maneuvers, they were opportunities for science. Even though BepiColombo's instruments couldn't be fully deployed while the spacecraft stack was still assembled, many sensors could still collect data during the close approaches. The first Mercury flyby occurred in October 2021, when BepiColombo passed just 125 miles above Mercury's surface. The second came in June 2022, the third in June 2023, the fourth in September 2024, the fifth in December 2024, and the sixth is scheduled for January 2025. Each flyby provided unique observations. The cameras captured images of previously unseen terrain, revealing new details about Mercury's heavily cratered surface. The spectrometers measured surface composition in regions that Messenger never studied closely. The magnetometers tracked how Mercury's magnetic field varies with location and time. And the particle detectors sampled the charged particles in Mercury's exosphere and magnetosphere, revealing how these tenuous environments respond to changes in solar activity. One of the most striking discoveries from the flybys came from images of Mercury's southern hemisphere, a region that Messenger studied less thoroughly than the North. The images revealed extensive, smooth plains, ancient lava flows that covered large areas billions of years ago. These volcanic plains are similar to the lunar Maria, the dark basaltic plains on the Moon's near side, but they appear to be even more extensive on Mercury. This suggests that Mercury was volcanically active for longer and more vigorously than some models had predicted. The flybys also revealed new details about Mercury's exosphere. This isn't an atmosphere in the conventional sense. It's an incredibly thin envelope of atoms that have been knocked off the surface by solar wind particles, meteoroid impacts, and solar radiation. The exosphere is so tenuous that atoms don't collide with each other. Each atom follows a ballistic trajectory, arcing up from the surface and falling back down like an incredibly high fountain. The composition includes sodium, potassium, calcium, magnesium, and other elements. BepiColombo's spectrometers detected variations in exosphere composition that correlate with surface features. Regions rich in certain minerals produce more of specific atoms in the exosphere. By mapping these variations, scientists can learn about surface composition even without directly observing the surface itself. The flybys also revealed that Mercury's exosphere changes dramatically depending on the planet's position in its orbit. When Mercury is at perihelion, its closest approach to the Sun, solar radiation is more intense and kicks more atoms off the surface, creating a thicker, more active exosphere. But the journey hasn't been entirely smooth. In 2024, BepiColombo encountered a propulsion issue that threatened to delay its arrival at Mercury. The spacecraft's ion thrusters, which use electricity from solar panels to accelerate xenon ions and produce thrust, developed reduced efficiency. After extensive analysis and testing, mission controllers determined that they could work around the problem by using different thrust configurations and adjusting the flight plan. This resulted in a delay of orbital insertion from December 2025 to November 2026, adding nearly a year to the already long journey. The delay was disappointing, but not catastrophic. It gave scientists more time to analyze data from the flybys and to refine their plans for the orbital mission. And it demonstrated the resilience of the spacecraft and the skill of the mission operations team, who managed to keep the mission on track despite a significant technical challenge. Once BepiColombo finally reaches Mercury in November 2020, the mission will enter its most exciting phase. The Mercury transfer module will be jettisoned, having completed its job of providing propulsion for the journey. The two orbiters, MPO and MIO, will separate and enter different orbits around Mercury. MPO will orbit in a polar orbit with a periapsis, its closest approach, of just 300 miles above Mercury's surface, and an apoapsis, its farthest point, of about 900 miles. This orbit will allow MPO's cameras to map the entire surface at high resolution, resolving features just a few meters across. The spectrometers will determine surface composition across the planet, identifying minerals and elements. A laser altimeter will measure surface elevation with centimeter precision, creating detailed topographic maps. And a suite of instruments will measure Mercury's gravitational field, magnetic field, and internal structure. MIO will enter a highly elliptical orbit ranging from 350 miles to 7,200 miles above the surface. This orbit is designed for studying Mercury's magnetosphere and exosphere. From its high apoapsis, MIO can observe the large-scale structure of the magnetosphere and how it responds to changes in the solar wind. The spacecraft carries magnetometers, plasma analyzers, and wave instruments that will characterize the charged particle environment around Mercury with unprecedented detail. The two spacecraft approach is powerful because it allows simultaneous measurements from different locations. When MPO is close to the surface, measuring the local magnetic field, MIO might be high above, measuring the global magnetosphere. When MPO is mapping surface composition on the day side, Mio might be studying particle precipitation on the night side. By combining data from both orbiters, scientists can build a comprehensive picture of Mercury as a system, understanding how the surface, interior, and space environment all interact. The nominal mission is planned to last 1 Earth year, which equals about 4 Mercury years, since Mercury orbits the Sun every 88 days. During this time, the orbiters will make thousands of observations, collecting more data about Mercury than all previous missions combined. If the spacecraft remain healthy and fuel reserves allow, the mission could be extended, potentially doubling or tripling the amount of data collected. Some of BepiColombo's most important objectives are specifically designed to test the hypotheses we've discussed. The precise gravity measurements will help determine the size of Mercury's core and whether it has distinct layers. The magnetic field measurements will test models of the dynamo and search for evidence of magnetic field reversals recorded in surface rocks. The surface composition mapping will look for signatures of the proposed diamond layer and will measure the distribution of carbon, sulfur, and other key elements. The thermal measurements will determine where permanently shadowed craters exist and will map the distribution of ice deposits with higher precision than MESSENGER achieved. BepiColombo will also address questions that MESSENGER couldn't answer. For example, MESSENGER had limited capabilities for observing Mercury's southern hemisphere because its orbit was optimized for northern hemisphere coverage. BepiColombo's more symmetric orbit will allow equal coverage of both hemispheres, revealing whether the southern hemisphere has the same types of features as the north, or whether there are fundamental differences between the two sides of the planet. Another key question is whether Mercury shows any signs of current volcanic activity. MESSENGER found evidence that volcanism continued until at least 3.5 billion years ago, much later than expected, but no definitive evidence of more recent eruptions. BepiColombo's high-resolution cameras and thermal sensors will search for very young volcanic features, perhaps even active vents releasing gas from the interior, though such activity is considered unlikely given Mercury's apparent geological quiescence. The mission will also investigate Mercury's hollows, strange bright depressions scattered across the surface that appear to be actively forming today. These features, first discovered by MESSENGER, are shallow pits with bright interiors and floors, often found inside impact craters or along crater walls. They appear to form through some kind of sublimation or erosion process, where material is being removed from the surface and carried away. The exact mechanism isn't clear, but it might involve the breakdown of sulfur-bearing minerals under intense solar radiation, or the release of volatiles trapped in the crust. BepiColombo will map hollows across the planet and monitor them for changes, potentially catching hollows in the act of forming or growing. As BepiColombo prepares for orbital insertion, anticipation is building in the planetary science community. Mercury has proven itself to be far more complex and surprising than anyone expected, and every new dataset brings fresh mysteries. What will BepiColombo discover? Will it confirm the diamond layer, or will it force us to abandon that hypothesis? Will it reveal the structure of Mercury's core and finally explain the offset magnetic field? Will it find new ice deposits, new volcanic features, new types of surface composition that we haven't imagined yet? The only certainty is that Mercury will continue to surprise us. This tiny world, scorched by the sun yet harboring ice, shrinking yet still geologically, active, metal-rich yet mysterious, has shown time and again that it doesn't conform to our expectations. And that's what makes planetary exploration so thrilling. We think we understand how planets work, we build models and make predictions, and then we actually visit these worlds and discover that reality is far stranger and more wonderful than our theories suggested. The bigger picture. Mercury's mysteries aren't just puzzles to be solved for their own sake. Every strange feature, every unexpected discovery, tells us something fundamental about how planets form, evolve, and die. Mercury is a laboratory for planetary science, a place where processes that might be subtle or hidden on other worlds are amplified and exposed. Consider what Mercury teaches us about planetary differentiation, the process by which planets separate into distinct layers. When a planet forms, it starts as a roughly homogeneous mixture of rock and metal. As the planet grows and heats up from the energy of impacts and radioactive decay, it begins to melt. The denser materials, primarily iron and nickel, sink toward the center, forming a core. The lighter materials, silicate rocks, float to the top, forming the mantle and crust. This process happened on all the terrestrial planets, but nowhere is it more extreme than on Mercury, where the metal core dominates the planet's mass and volume. Understanding why Mercury differentiated so completely helps us understand differentiation in general. Was it purely a matter of temperature and density, or did impact processes play a role? Did the timing of differentiation matter, happening earlier or faster than on other planets? The answers have implications for all rocky planets, including the thousands of exoplanets we've discovered orbiting other stars. Many exoplanets orbit very close to their host stars, even closer than Mercury orbits the Sun. These so-called hot Jupiters and hot Neptunes experience extreme temperatures and radiation that rival or exceed what Mercury endures. By studying how Mercury responds to its harsh environment, how its surface weathers, how it loses and retains volatiles, how its interior evolves under intense heating, we gain insights that apply to these distant worlds. Some exoplanets are thought to be super Mercuries, rocky worlds with unusually high metal content. These planets might have formed through processes similar to what shaped Mercury, either selective vaporization in the hot inner regions of their planetary systems, or giant impacts that stripped away rocky mantles. When we detect these planets through their transits across their host stars, or through the wobbles they induce in their star's motion, we can measure their masses and sizes. If a planet is much denser than expected for a normal rocky composition, it might be a super-Mercury with an oversized iron core. Mercury also teaches us about magnetic dynamos. For decades, planetary scientists thought that only large planets could sustain active dynamos. Earth has one because it's big enough to retain a hot interior over billions of years. But Mercury, tiny Mercury, also has one, operating under conditions very different from Earth's. This tells us that dynamos can work in small bodies if the conditions are right, perhaps a sulfur-rich core that stays molten, perhaps a thin mantle that allows efficient heat extraction, perhaps some other factor we haven't identified yet. This has implications for asteroids, dwarf planets, and even some large moons. Could any of these bodies have had active dynamos in their past, or could some even maintain them today? Europa, Jupiter's ice-covered moon, is thought to have a subsurface ocean of liquid water. Could this ocean, combined with a partially molten rocky interior, generate a magnetic field? Ganymede, another Jovian moon, actually does have a magnetic field, making it the only known moon with an active dynamo. Understanding Mercury's dynamo helps us understand Ganymede's, and might point the way to discovering magnetic fields around other surprising bodies. The discovery of ice on Mercury also has broader implications. If the hottest planet can preserve ice in permanently shadowed craters, then ice might be far more common across the solar system than we realized. The Moon has ice in its polar craters. Mars has ice in its polar caps and buried beneath mid-latitude regions. The moons of the outer planets are largely made of ice. Even some asteroids appear to have ice beneath their surfaces. Ice is everywhere, and understanding how it accumulates, how it's preserved, how it interacts with its environment, is crucial for understanding the distribution of water throughout the solar system, and potentially for identifying resources for future space exploration. Mercury's shrinking, its ongoing contraction driven by interior cooling, is a preview of the fate awaiting all rocky planets. Earth is also cooling, though much more slowly because of its larger size and the insulating effect of its thick mantle. Eventually, Earth's core will solidify, convection will cease, and the magnetic field will shut down. Eventually, Earth's interior will cool to the point where volcanic activity stops and the crust becomes a rigid shell, wrinkled and cracked like Mercury's. This won't happen for billions of years, and other factors like the Sun's evolution into a red giant will likely intervene first, but the fundamental process is the same. Mercury shows us Earth's distant future, a preview of what happens when a rocky planet finally cools and dies. The volcanic history of Mercury also informs our understanding of how planets transition from active to dormant. Mercury had extensive volcanism early in its history, with vast lava plains covering much of the surface. But volcanic activity shut down relatively early, around 3.5 billion years ago, and there's no evidence of significant volcanism since. What changed? Did the mantle cool below the melting point? Did the crust thicken to the point where magma could no longer reach the surface? Did changes in Mercury's tidal heating or core dynamics affect the mantle's ability to generate melt? Understanding this transition helps us understand similar transitions on other worlds, including Mars, which also had extensive early volcanism that eventually ceased. There's also the question of comparative planetology, understanding the solar system's terrestrial planets as a family of related but distinct worlds. Mercury, Venus, Earth, and Mars all formed in the same region of the solar nebula from similar materials. Yet they evolved into radically different worlds. Mercury is bone dry with no atmosphere. Venus has a crushing, scorching atmosphere and possible ongoing volcanism. Earth has liquid water, plate tectonics, and life. Mars is cold and desert-like with a thin atmosphere and ancient river valleys. Why did these worlds diverge so dramatically? Part of the answer lies in size. Larger planets retain their heat longer, sustain geological activity longer, and can hold on to their atmospheres more easily. Earth, the largest of the terrestrials, is still fully active. Mars, smaller, is largely dormant. Mercury, smallest, has minimal geological activity beyond its ongoing contraction. But size isn't the only factor. Venus is nearly identical in size to Earth, but evolved very differently, perhaps because it lacked Earth's magnetic field, or perhaps because it was slightly closer to the Sun, triggering a runaway greenhouse effect that boiled away any oceans it might have had. Mercury, as the smallest and the closest to the Sun, represents one extreme of the terrestrial planet spectrum. By studying this extreme, we bracket the range of possibilities and better understand the factors that determine a planet's evolution. Every measurement of Mercury's composition, Every observation of its surface features, every data point about its interior structure, contributes to our broader understanding of terrestrial planet evolution. Looking forward, the knowledge we gain from Mercury might influence how we search for habitable worlds around other stars. If we understand the processes that made Mercury so dry and hostile, we can better evaluate whether planets orbiting close to their stars could somehow retain water and maintain habitable conditions. If we understand how Mercury's magnetic field operates despite the planet's small size, we can better predict which exoplanets might have protective magnetic fields. If we understand how Mercury preserves ice in shadowed craters, we might identify similar cold traps on exoplanets where volatiles could accumulate. Mercury is a window into planetary processes operating under extreme conditions. It's a test case for our theories, a place where predictions can be checked against reality. And it's a reminder that every world in the solar system has its own story to tell, its own unique combination of formation history, composition, and evolution that has shaped it into the planet we observe today. Conclusion. Let yourself settle back now, feeling the weight of the cosmic journey we've taken together. We've traveled to the smallest planet in our solar system, a world that seems at first glance to be simple, just a scorched ball of rock orbiting close to the sun. But as we've discovered, Mercury is anything but simple. It's a world where contradictions pile upon contradictions, where every answer reveals new mysteries, where the familiar rules of planetary science are pushed to their breaking points. We've seen ice on the hottest planet, preserved in eternal darkness even as the surface just miles away bakes at temperatures hot enough to melt metal. We've explored the possibility of a diamond layer wrapping around Mercury's core, a shell of crystallized carbon that might influence the planet's magnetic field and thermal evolution. We've watched a planet shrink before our eyes, its surface wrinkling and cracking as the interior cools and contracts. We've puzzled over Mercury's enormous iron heart, trying to understand how this tiny world ended up so metal-rich. We've marveled at the magnetic field that shouldn't exist but does, weak yet persistent, offset and strange. We've traced BepiColombo's long journey to Mercury and looked forward to the discoveries that await when the mission finally enters orbit. Mercury challenges us. It defies our expectations and forces us to think harder, to question our assumptions, to remain humble in the face of nature's complexity. This little world, so close yet so difficult to reach, so small yet so full of mysteries, is a reminder that the universe doesn't care about our theories. It simply is, and our job as scientists and as curious humans is to observe, to measure, to wonder, and to try to understand. As you drift off to sleep tonight, let your mind wander across Mercury's cratered surface, through its diamond-laden depths, around its enormous metallic core. Think about the ice hiding in the shadows, ancient water and organic molecules preserved for billions of years. Think about the planet shrinking, millimeter by millimeter, year by year, its crust buckling under the stress. Think about the magnetic field lines stretching out into space, creating a tiny bubble of protection against the relentless solar wind. Think about BepiColombo, even now making its final approaches before orbital insertion, ready to reveal Mercury's secrets in unprecedented detail. And remember, this is just one planet, one world out of countless billions in the universe. If Mercury, our closest planetary neighbor aside from Venus, can harbor such mysteries, what wonders await us on the worlds we've barely glimpsed? the exoplanets orbiting distant stars, the moons of the outer planets, the dwarf planets in the Kuiper Belt. The universe is vast, ancient, and full of surprises, and we've only just begun to explore it. Sweet dreams, fellow travelers. May your sleep be as peaceful as the eternal night in Mercury's polar craters, and may your dreams be filled with the wonders of the cosmos. If you enjoyed this journey to Mercury, please take a moment to like this video and subscribe to the Science Pillow. Your support helps us continue exploring the universe's greatest mysteries, one relaxing story at a time. Until next time, keep looking up, keep wondering, and keep dreaming. Sleep well.